Uh, Hello all. There seems to be some technical glitch regarding my screen sharing. I hope it's still audible. I hope my audio visual feed is still available. So let me try and share my screen. Hold on one second. Yeah, so let me know if it is visible or if uh, in case if you are facing any sort of difficulties.
I think it is visible.
All right. Okay. Thank you. So, hello all. I am Isaac John. I will be the TAs who will be handling the weekly live tutorial sessions on mechanics and control of robotic manipulators. So, I hope you have gone through all the videos regarding week one lectures. Basically, IIT Palakkad is offering two courses on robotics, two courses on mechanics of robots. So the first course is actually the mechanics and control of robotic manipulators. And the second course is on wheeled mobile robots. So that will be floated in the upcoming semesters. So we keep on having these two courses alternating. So yeah, so without much further ado, let's get on with the session. So the way I have designed this tutorial session is basically into two parts. I've divided this tutorial session into two parts. So the first part, we'll have a brief overview of all the topics that we have discussed. Hello? Someone wants to speak up. Is there any doubt that you have? Okay, so yeah,
I have a question. This call will take place quickly.
I'm sorry, I couldn't follow you.
This call will take place quickly every week. This week, just only week this week.
You want any clarifications? I'm not sure if I quite follow you though. If you need any clarifications, please let me know. Otherwise, I'll just continue with the session. Yeah, I've got a message from the chat. I've got a question regarding whether this course will take place weekly. So this live, yes. So the live tutorial sessions will have this every week. Every week on Tuesdays from 6 p.m. to 8 p.m. local time. Each week we'll basically have a discussion about the topics that we have discussed, and then we'll also solve some sample questions, which would be very similar to the questions that you can expect for the quizzes. So I hope you have already seen the questions, which is as part of the quiz, because I suppose the deadline is until 8th of August, until the first or second week of August. So until then, you can attempt the quizzes, and you can submit the solutions any number of times. The questions that we'll be discussing would be very similar to the quizzes. You can expect all sorts of questions during these sort of tutorial questions. Okay, so continuing the topics for week one, we start by a very brief introduction to robot mechanics. What we mean by robot mechanics, and what are the problems that we try to solve in robot mechanics. Then we basically see the difference between two major problems, from robot mechanics, what we call as forward and inverse kinematics. Then we also see how we describe position and orientation of points, frames of references. How do we describe that? And then we talk about transformation matrices, which basically combines information regarding position and orientation of rigid bodies. And then we also see a case of compound rotations, where you have simultaneous rotations about multiple axes, and how to represent them using the transformation matrices. So yeah, we'll just start by talking about brief definitions of the term called robot, because this is what we are focusing on for this course. So according to the American Robotic Industries Association, an industrial robot is a reprogrammable multifunctional manipulator designed to move materials, parts, and tools or specialized devices through variable programmed motions for the performance of a variety of tasks. So the key difference, or the important term that you have to notice here is that an industrial robot is basically a mechanical system that we can reprogram, right? Unlike if you take a look at any machinery from an assembly line of a vehicle, they are not reprogrammable, right? Most of the things that you find in industry, they are basically fixed. They are designed to perform a single task. But in case of a robotic system, the entire mechanical manipulator or the entire mechanical architecture can be reprogrammed to a, uh, to a variety of tasks, to a variety of applications. For example, you can task it to pick one object and place the same object into a different conveyor belt. Maybe you can use the same robot for spray painting applications. So it's very agile in that regard. Multiple ways you can deploy the same robotic manipulator into a variety of different tasks. And now a more modern definition of robot. It says a robot is an intelligent, physical or virtual device that is capable of doing a task autonomously with or without guidance. So earlier we were discussing about something called the manipulator.
I have a quick question.
Yeah.
Usually, how do we determine the coordinates of the object to be picked or placed in environment?
Yes.
Can you hear me?
Usually, yeah, we have the position of an object to be picked up. Yes, that is correct. That is what a manipulator does, right? Like if you want a manipulator to pick up an object, the coordinates of that object, be it position or the orientation, will be fed back to the manipulator, and the manipulator will accordingly, position itself so that it can correctly grasp or acquire that object and place it somewhere else. That is what a manipulator does. But in modern definitions, there does not need to be a physical manipulator. It can be a virtual entity as well. For example, if you know about chatbots, what we usually see in customer services these days. So if you want to talk to a customer service, usually these days we won't get to talk to a human being right away, right? We have to first talk to a chatbot, and more often we'll be able to find the chatbot will be able to give you the solutions, or it'll be able to troubleshoot our issues even before diverting us to a human being. So that according to a modern definition, a robotic system or a robot does not really have to be physical. It can also be a virtual entity. And from the framework of this course, we will be only talking about robot as an electromechanical machine or a mechatronic system with sensors, electronics, and guided by computers and controllers. So from the perspective of our course, the primary component of a robot is a mechanical system. For example, if you consider a robot with just two links, like so, this can actually be considered as a robotic arm, right? I'll label this as link 1. I'll label this as link 2. And the first link is actually mounted or fixed to the ground using a fixed link. And then you can connect it using some revolute joints. And then that would be the primary component of a robotic system. And then we would have to embed the mechanical architecture with sensors and actuators. Maybe you can call the motors as the actuators, probably here and here. so that we'll be able to control the motion of the robot. And then we also need some sensors, to detect its current position. So one typical example of a sensor that we commonly use to determine the position of a robot, we call them as encoders, right? We will keep that go in the same axis as that of the motors, so that we'll be able to know how much degrees the joint has rotated. Right. So we'll basically combine a mechanical system with sensors and actuators. And using the information from the sensors and actuators, we'll be able to guide the set mechanical system to whatever position that we want to move it. All right, then we talked about the 4Ds of robots. This basically gives an idea on where where we would be deploying robots. So typically, we would deploy robots in tasks that can be classified as dull, dirty, dangerous, or difficult. So I suppose these are all self-explanatory, right? So if a task is very dull for a human being, because of its repetitiveness, or maybe because of its physical exertion, doing repetitive tasks for an extended period of time could be a very dull task for a human being to perform. And eventually, the efficiency of a human being in performing the task repeatedly would drop. So you could employ a robot to perform tasks that are repetitive, and at the same time, you can have a consistent efficiency, which would be much more, much higher than what a human being can realize. And then you can maintain that high efficiency all the time, at a constant level without, seeing any drop on the efficiency. And then there are tasks that would be deemed dirty, for a human being. So these days, in a lot of developed cities, you would see robots, handling the cleaning of footpaths, sewages, manholes, all these sort of things, which are typically considered as a job, a bit dirty for human beings to perform. And then again, there are tasks which could be dangerous, if you deploy a human being for the set task. Maybe, for example, if there is any radioactive leak in any of the power plants, nuclear power plants, in order to do some initial evacuation or to contain the leak, uh, some sort of intervention has to be made. So instead of sending human beings, you can actually send robots, so that the fallout can be contained within a safe zone. And then there are tasks which is typically difficult for a human being to perform. We can also deploy robots for that task. But then if a task, most of the time, this may not probably work, because, as you know, a human being is actually a very advanced or very complicated uh, mechanical system, right? We can do so many things standing just on our 2 feet. But a lot of robots, they actually struggle to stay balanced, with their 2 feet, and their applications are also very limited because of issues related to stability due to computational costs and all those things. So this may not be applicable in a lot of situations, but more or less for it's still a valid choice, so that we have to consider robots if the task seems too difficult for human beings to perform. And now we move on to more focused area. Until now, we have been talking about robots and what we mean by a robot, and when to deploy a robot. And now we talk about something called effector, right? So effector is a component of a robot, one of the most important component of a robot that can have an effect on the environment. So the basic definition is like so. An effector is any robot or a robotic device that has an effect on the environment. So what you see in all these images, they are all effectors, various kinds of effectors, right? They all have, due to their motion or due to their interaction with the environment, they have different effects on the environment. So like we can further classify this effector into three categories mainly. So over to your left-hand side, we call these sort of effectors as the manipulators. So this would be our focus for the entirety of the course. And to the middle of your screen, we call them this as mobile robots. And to the right of your screen, this is basically a hybrid solution. You have a mobile robotic base, and also on top of the mobile robot, you have a manipulator mounted on top of this. See, you can call them these solutions as vehicle manipulators. Or even you can also call them as mobile manipulators. So the key distinction between manipulators and mobile robots is that in case of a manipulator, you have the base fixed to a location, right? So if I define a coordinate system, maybe a global coordinate system like so, with z-axis pointing upward, x-axis pointing to the right-hand side, and maybe the y-axis pointing out of the plane. I'll call this as the y-axis, or maybe it should rather be going in the other direction. If you follow the right-hand thumb rule, the y-axis should be like so, going out of plane. All right. So in case of a manipulator, the base is always fixed to the ground, and all of these links will have relative motion with respect to each other. So if you consider this to be the first link, whatever I'm currently shading, it can rotate about the vertical z-axis, and the second link here, can rotate about this axis. It can rotate like so, back and forth. And there is also a third link over here that can also rotate about this axis, in this direction, to and fro. And at the end, you have a wrist that can rotate in three directions, one about this axis, one about this axis, and one more, a small rotation about this axis. And at the end of this effector, you can attach probably an end effector, what we call an end effector. Maybe it could be a gripper like so. You can mount a gripper so that it can be used to grasp objects, right? So this the vices of the gripper can open and close. Or if you want to use it for a different application, you can probably use it for spray painting application, where you have a spray painting gun like so. Or you can you can attach a welding apparatus or a welding rig at the end of the robotic arm, so that it can be used for automated welding processes. So basically, in case of a manipulator, the effect on the environment, the effect of the manipulator that has on the environment, is the movement of the objects around, right? So in case if the manipulator has a gripper, or if there is an obstacle or an object in its workspace, the effect on the environment this manipulator would be having would be the motion of the objects around it. The robot can pick this object, it can place it in some other coordinate, or it can rotate the object, whatever be the case. So the effect would be the motion of the objects around the manipulator. But in terms of a mobile robot, you can actually see that the mobile robot interacts with the environment using the wheels over here, right? So the effect the mobile robot has on its environment would basically be the motion of the mobile robot itself, right? So if some force is exerted through the wheels, the ground will exert equal and opposite reaction onto the wheels, which would result in the motion of the mobile robot, right? So the effect of mobile robot on the environment would lead to the motion of the mobile robot. Whereas in case of a mobile manipulator, it would be the combination of two. The effect, there are combinations of effect on the environment, and the resultant reaction would be the motion of the mobile robot as well as the motion of the objects within the environment. So that is the difference between how you classify a manipulator or a mobile robot. It all depends on the effect the device has on the environment. And for this course, we would be focusing more on manipulators. Right. So now we look on to the different types of manipulators. So over to your left is a class of manipulator, what we call as serial manipulators. Right. The reason we do so, the reason we call them as serial is because the links are attached serially, right, one after the other. So there could be one link like so, the base link here, and to the base link you have another link attached serially, like, and to this link another link is attached. So the links are attached serially one after the other. So if you draw schematic, it'll look something like this. So you have a base like so, and you have one link attached to the base. I label this as link 1. And at the tip of the first link, you will have another link like so, link 2, so on and so forth. You can have any number of links, right? And at the very end of the farthermost link, you can have a gripper or any sort of end effector. So as you can see, the links are attached serially, one after the other. That is what we call as serial manipulators. And over at the middle of the slide, you can see something with multiple legs, right? You have a platform at the top, you have a ground over here, and this platform and the ground is connected using multiple legs or multiple links, right? This is one link, this is another leg, this is another leg. So you can actually see in this figure, there are six such legs, right? And these sort of manipulators are called parallel manipulators. Right? Because here in this case, you can actually see that the top platform and the base are connected using parallel legs. And you can control the position and orientation of the top platform using by controlling the length of these legs, individual legs. So like these are telescopic legs. There is a prismatic joint in between, so that if you extend or contract this prismatic joint, the position and orientation of the top platform would change. We would use these sort of mechanisms in aircraft simulators, where the people would be this would represent the cockpit, and people would be staying inside this capsule, so that it will basically give a real life simulation of a aircraft cockpit. So depending upon the inputs that the pilot gives, the motion, the platform will simulate the appropriate motion. So these days, these are not only used in cockpits, they're also used in race car simulators. The racing drivers, if they want to train or if they want to test a new circuit, they would use these sort of platforms, and the driver would sit on top of this. The platform would mimic the seat of a race car, and the driver can actually sit, on top of the platform. And depending upon the input that the driver would give, the platform would simulate the appropriate motion, depending upon how fast it's going, whether if he's turning or whether if he's braking or accelerating. Those sort of motions would be replicated by the parallel manipulator. And then over here you have something called a hybrid case. For the first part of the mechanism, you have a serial manipulator, and at the very distal end of the mechanism, you have a parallel robot. So this over here is a parallel manipulator that is being attached to a serial manipulator over here. This is a serial manipulator. So there are some inherent differences between serial and parallel robots. So in serial robots, the heaviest part of a serial robot are the actuators or the motors. So compared to the weight of the link, the actuators or the motors are much more heavy, right? So the majority of the weight that robot has to carry is its own weight, right? If you consider no payload, the motor at the very base would have to carry the weight of all the subsequent links, that is lying on top of it. And as a result, since it is carrying so much weight, the accuracy of a serial robot is a bit limited, due to the deflection, due to hanging, and all those sort of things. So inherently, the accuracy of serial manipulator is a bit limited. But then they have a very large range. They can, if you consider your arm as a serial manipulator, you can actually see how far you can reach your arm, how far you can extend your arm. So in that regard, serial manipulators have very large workspace. But in case of parallel manipulators, it's quite the opposite, right? All the heavy actuators are close to the base. There won't be any actuators at the top. All the actuators are close to the base. So the moving mass or the moving inertia are very close to the base. And as a result, they have very high accuracy. And also due to the fact that there are multiple legs connecting the end effector and the ground, the errors are not accumulated, right? So the total error would be only the intersection of all the errors, it won't get accumulated. The errors are not getting accumulated. But the main limitation of a parallel manipulator is that their workspace is a bit small compared to serial manipulators, right? Inherently, they are a bit small. So one example I can probably give you is if you try to hold both of your arms together and see how far you can reach while holding both of your arms, it'll be a bit lesser compared to how it'll be lesser compared to when the case when you fully extend just a single arm, right? A single arm can extend much more further than when you try to extend with both of your arms clasped together. So that is the difference between a serial manipulator and a parallel manipulator. Yeah, now we talk about a few key definitions or a few key terms regarding the manipulator. So essentially, yes, sorry, yes. Yes.
The explanation is great overall. I just had two doubts about the meeting itself. First, will the recording be provided to us?
Yes, the recording will be provided. The problem is that I'm having some sort of an issue with today's recording. Okay. Because I'm doing it in a different way that I'm supposed to do. I cannot record it from my PC.
On your tablet.
It's on my tablet. I'm not. It should be accessible, but if it is there, it'll be provided.
Okay, and also, actually, I was 5 minutes late to the meeting, so was there any attendance form given?
No, there are no attendances. There is no attendance for the meeting.
Okay, got it. Thank you.
Yeah. Okay. All right. So now we talk about manipulators. Some key terms regarding manipulators. So manipulator is nothing but it's a system of bodies or links arranged or connected as a chain with the help of joints. So we have discussed this earlier. Like we have a series of arms or series of rigid bodies. Those are which are connected by joints, right? We'll talk about different kinds of joints, maybe in the course of this lecture, maybe maybe in the upcoming weeks. But mostly we'll be dealing with revolute joints or hinge joints, which has a single degree of freedom, as well as a prismatic joint, a sliding joint that also has a single degree of freedom. Right. Then another term that we would be using recurringly for this course is something called a configuration. Right. So the definition of configuration is a complete specification of location of every point on the manipulator. So for example, if we consider a manipulator with just two links, right? I'll show one example. So if this is the first link, like so, and if this is the second link, and the big circles are used to represent the motors actually, and the first joint is actually fixed. The motor is actually rotating on a fixed hinge. This is the second link. So typically, configuration specifies the location of every point of a manipulator. So the diagram I have actually shown here is only valid at this particular instance. Maybe at a different instance, it can be like so, right? Or in some other instance, it can be like so, right? So so if you want to define a configuration, each and every point of the robot will have to be you will have to define each and every point of a robot at any given instance. So in case of a serial robot, you can actually see that there are two inputs that you have to give, to fully define the configuration of a robot. The first input is over here on the first joint. So I'll represent it as with a variable called as maybe theta1, and maybe the second joint I'll probably represent it with another angle called theta2, right? So depending on what theta1 and theta2 is, you will be able to fully define each and every point of this robot, right? So if you have a global coordinate system like so, the x-axis and probably the y-axis, at all instants of time, you can define the coordinates, the x and y coordinates of any point using this theta1 and theta2 coordinates. So whereas in the case of a 4-bar mechanism, maybe a closed loop mechanism like this, you will have 4 links, but it will be connected as a closed loop like so. So you will have one motor over here, another motor over here, another motor over here, another motor over here. So you basically have 4 such links. So in this case, you only require a single join variable or a single variable so that each and every point of the robot can be fully defined, right? So we'll see all these cases when we are discussing the forward and inverse kinematics. How you can define the entire configuration of a robot with just 2 variables in case of a serial manipulator. But in case of a parallel manipulator, it becomes more complex actually. So there are, as you can see, there are 4 bodies, but you are basically specifying the configuration of all 4 bodies just by a single input. Right. So that's about configuration. Specifies the location of every point on the manipulator, and then the next term is called the workspace. This is also a very important aspect or a very important feature in a robotic manipulator. This is the total volume swept out by the end effector as the manipulator executes all possible motions, right? So if you have a robotic manipulator with 2 joints, and if you consider the tip of the manipulator as an effector, maybe a gripper, So the set of all points that can be achieved or realized by the tip of the robot is called, is called the workspace of the robot. So to understand or to visualize the workspace, you have to rotate, in this specific case, you have to rotate this theta1 joint uh, in all possible uh, rotations. Maybe this joint can rotate from 0 to 360, and same goes for theta2. Maybe it can also rotate from 0 to 360. So if you, combine all the rotations, for all the two joints, the net volume or the net cloud of points that the manipulator can realize is called the workspace of the robot. Then you can also classify the robot's workspace into two. The first one is called reachable workspace, and the second one is called the dexterous workspace. So the basic difference between reachable and dexterous workspace is this. In case of a reachable workspace, these correspond to a point where a robot's arm or a robot's tip can just reach, at any orientation. So, like for example, if you consider your arm as a robotic manipulator, if you try to fully stretch your arm, you can only reach the farthest point with a single orientation, right? Maybe if you try to fully extend your arm, you can only reach that tip with a single orientation. You cannot reach it in any other orientation. But if there is any point inside the workspace, for example, if you consider this finger, I hope you can see that, if you consider my left finger or left hand finger as the point that you want to reach, and my right hand finger, as the tip of the robotic arm, you can basically reach the object in any possible orientation. Same position, but any arbitrary orientation. So those sort of workspaces are called dexterous workspace, right? Whereas in reachable workspace, you can only reach by a single or a very limited set of orientations, whereas dexterous workspace are points where infinite number of orientations are possible. So those are the key differences regarding the reachable and dexterous workspaces. And then we would also talk about one key definition. It's called the degree of freedom. So throughout the course, you will be actually hearing this term called degrees of freedom. And this is all an important aspect based on which how you would classify the robots, or how you would describe a robot. The fundamental way to describe a robot is by using its degrees of freedom. So the definition says degrees of freedom are the minimum number of independent variables required to describe a system, right? So I hope you can recall, when we discussed the configuration of a robot, in case of a serial robot with two links, we used two variables, right? We used two variables, theta1 and theta2, to describe its full configuration. So in that regard, that robot basically has, you can say that a robot has 2 degrees of freedom because we need two variables to describe its configuration. Whereas in the case of a parallel robot, it would be fewer, right? It would be fewer than the number of links. You would only probably need a single variable to describe its entire configuration. So that's what it says. It says the minimum number of independent variables required to describe a system. And then another term called degree of manipulability. It's essentially the number of controllable inputs or active joints. So in terms of manipulators, these two definitions does not make much of a difference. Degrees of freedom and degrees of manipulability corresponds to the same thing. But in case of a mobile robot, these two definitions can actually change. There is a different meaning to a degree of freedom, and degree of manipulability could be something else. But in robotic manipulators, both of them corresponds to the same value. But we will mostly stick with degrees of freedom definition. So yeah, we'll see. We'll familiarize ourselves with all these definitions. As we go through the contents of this slide. Yeah. Now we move on to the aspects on robot mechanics. So if you talk about mechanics, kinematics is actually a part of mechanics actually, where in kinematics we just study the motion without considering the forces or efforts that cause the motion, right? So in case of kinematics, we are only interested in if you rotate the joint by probably 2 degrees or 3 degrees, what will be the configuration of a robot? We are not really bothered about how the forces actually that causes this sort of motion. So like for example, if you simply try to drop a manipulator under the influence of gravity, most likely it will collapse, right? Unless you are energizing the motors, it will most likely collapse. But then in kinematics, we are not really bothered about the effect of forces. We are just trying to study the motion, depending upon, we are just trying to figure out the relation between the inputs and the outputs, right? So in a robot, we give inputs to the motors, and the output is, what that robot is executing. So we are only interested to study the input-output relations. So there are two problems in kinematics. So the first problem is called forward kinematics, and the second problem is called the inverse kinematics. So with an example, I'll try to elaborate what forward and inverse kinematics basically mean. So as before, I'll replicate a robot with 2 links. We call this an 2R robot, right? I'll just write it over here, 2R. This R basically stands for revolute or rotary. 2R manipulator. The reason we call this as a 2R manipulator is because it has 2 revolute joints or 2 rotary joints, like so. So I'll call this as R1 and I'll call this as R2. And at the end, you have a gripper, actually. I'll just write it over here. A gripper, like so. So as I've said earlier, you can give inputs to the motors. So maybe I'll represent the input to the motors using the 2 angles. Maybe I'll call this as θ1. And I'll call this angle as θ2. Right? And I'll also depict the positional coordinates of this gripper as x and y using the Cartesian x and y coordinates, right? So in the forward kinematics problem, what we do is that if you are giving any combination of θ1 and θ2, if you are giving any inputs to the motors, what would be the position of the gripper, or what would be the position of the tip of the robotic arm? That is what forward kinematics is trying to do. So I'll just write it over here. You have θ1 and θ2 as inputs. And using a forward kinematic modeling, you will be able to get the outputs, maybe the x and y coordinates of the robotic arm. These are outputs, right? So typically, we call these angles, the inputs to the motors, as joint variables. We would be using this terminology throughout the course. We would call this as joint variables, because these corresponds to the angle these the joints rotate, right? If there are 2 links, this could be the first link and this could be the second link. The rotation by which the links rotate about its own joint corresponds to the joint angle, and these inputs are provided by the motors. So we call them as joint variables, or another term is configuration variables. And the coordinates that we use to represent the position of the end effector or the gripper, we call them by the name task space variables. Or you can also call them as operational space variables. Right? So for any given theta1 and theta2, what will be the x and y coordinates? Right? So this is like a simulation of a robot, right? You're trying to see how the robot reacts or how the robot responds if you try to give the inputs to the motors. Right? So that is more or less similar to how you simulate a robot, or just to understand how a robot works. That is about forward kinematics. But in case of inverse kinematics, it goes from the opposite direction, right? So you give the final position of the end effectors as maybe some desired position of end effectors as your inputs. Maybe this is the task space variables. And using an inverse kinematics modeling, you will be able to figure out how much you have to rotate, the two motors. So this is like, if you want to control a robot, you have to solve the inverse kinematics problem, right? Suppose you want your gripper to move to a position, right? To pick up an object or to maybe to drop an object. For example, I'll give this blue dot as X desired and Y desired. This is where you want your robotic arm to move. So in that case, what should be the joint angle, or what should be the inputs that you should be giving to the motors? So solutions to such problems would be obtained using this inverse kinematic scheme, right? So in case of a manipulator like this, if it wants to reach this orientation, it can go like this, right? So with the correct representation or with the correct joint angles, you can actually reach that final goal position. So that is what we use inverse kinematics for. So that is the difference between forward kinematics and inverse kinematics. Forward kinematics is like simulating the robot, right? For any pair of joint angles, what will be the output that you'll be getting? But inverse kinematics is like, it's trying, you are controlling the robot, to achieve a desired position, what should be the inputs that you should be giving to the motors? That is inverse kinematics. Right. Now we move on to describing positions and orientations of the robot. So this is actually, this section is actually very important because we use some methodologies, or we use some standard practices to describe the position and orientation of the robot. And most of the robots that we are dealing with, they have spatial motion capabilities. They can move in X, Y, and Z axes. They can also rotate about the three axes. So their motion is actually very complex. The motion between two rigid bodies can be very complex. And we want to find a unified standard way to describe the position and orientation of multiple rigid bodies. So the easiest way to represent complex motion of rigid bodies is by attaching frames, on the rigid body. So like, for example, I'll show one example. If I have two rigid bodies, let this be one rigid body. It has two joints, at two of its ends. You have another rigid body like so. So imagine you can consider these to be floating in space, right? They are not connected with each other. They are basically floating with each other, floating in space. So I label this as rigid body 1. I label this as rigid body 2. But in robots, these rigid bodies would be connected. That is a different issue, right? So at the moment, we'll consider them to be disconnected. How do you represent the relative motion between these two rigid bodies? So the easiest way to represent the motion of two rigid bodies is that you can assign coordinate frames on the rigid bodies. Maybe I'll attach a coordinate frame like so. Let this be the x1 axis. Let this be the probably, yeah, y1 axis, and this be the z1 axis. And on the second body, I'll attach another frame of reference, maybe x2, y2, and z2. So what we are essentially doing is that to represent the complex motion between two rigid bodies, we are essentially replacing the rigid bodies by frames, by coordinate frames. And then we can try to find out the relationship between the relative position and relative orientation between two of these frames. So if you know the relative information between the two frames, any point within any of the rigid bodies can be fully determined, right? Since this frame is attached to the rigid body, you will get to know each and every point within that rigid body, with respect to this frame of reference. And similar case, for the first link, you will be able to identify the location and orientation of each and every point with respect to the frame of reference that is fixed on the first link. Right? So that is why we are replacing, instead of rigid bodies, we are replacing or we are representing them using coordinate frames. And in case of a multi-link robot with multiple links, we are trying to find out the relationship between multiple frames of references based on what their relative positions are and what their relative orientations are. So we begin with the basic idea. If you have a frame of reference like so, maybe it could belong to a robotic arm, or maybe it could belong to a robotic link, but we'll just ignore that aspect for the time being. If you have a frame of reference like so, how would you describe the position of a point, of any random point? You can do so by this vector representation, right? If you move x-axis along the px units along x-axis, if you move py units along the y-axis, and if you move pz units along the z-axis, you will be able to find out, or you will be able to reach this point P. Right? So the position can be represented using just three coordinates, px, py, pz. That's fairly straightforward. Right, that's about position. Now the challenge comes on how you can define orientations between two frames of references. So here you can see two frames actually coinciding with each other. So the first frame is labeled as frame A with axes as XA, YA, and ZA. So you can consider the first frame to be, fixed to the ground, always stationary. And you can consider the second frame, XB, YB, and ZB to be a moving frame. It moves with respect to the first frame. And you can also see that there is actually an orientational difference between two of these frames, right? So if you observe closely, you can actually see that XA and XB are aligned with respect to each other, right? XA and XB are aligned with respect to each other. YB makes an angle theta 1 with respect to YA. So I'll label this as theta. So this angle becomes 90 minus theta. And by extension, this becomes theta. And this angle becomes 90 minus theta. I hope it is clear. If there is any doubts, please let me know. Right? So we define or we represent the relative orientation between the two frames of reference using something called, a rotation matrix. Right? Rotation matrix to represent the relative orientation between the two frames of references. So basically, in this figure, we are actually representing the rotation about x-axis, right? A pure rotation about x-axis. So if you're rotating frame B with respect to, frame A, with respect to only the x-axis, the x-axis of XA and XB would be still coinciding, but YA and YB would be oriented at an angle theta. ZA and ZB will also be oriented at an angle theta. So I'll explain how we can populate the elements of a rotation matrices. These basically correspond to the dot product between the unit vectors of the two frames in question. So I'll give a general outline of how you can populate the elements of a rotation matrix. So in the first column, it basically is the dot product that the XB axis makes with respect to XA, YA, and ZA. So the first column would be XB dot XA. The second element would be XB dot YA, and the third column would be XB dot ZA. And the second column would be YB dot XA, YB dot YA, and you have YB dot ZA. And the third column would be ZB dot XA, ZB dot YA, and ZB dot ZA. Right? So in the first column, you can have XB, YB, ZB, orientation of XB with respect to the global or the fixed coordinate frame. And for the second row, you have the orientation that YB makes with respect to the global XYZ coordinates. And for the third column, you have the angle ZB makes with respect to the global XYZ coordinates. And you all know that the dot product between two unit vectors, maybe x1 and x2, if you consider these to be unit vectors, the dot product expansion would be x1, x2 cos theta. If theta is the angle between these two unit vectors, the expansion of this unit vectors would be x1, x2 cos theta. But since these are unit vectors, their corresponding magnitude is unity. So the only thing that remains is just the angle between these two unit vectors. So the same thing applies here as well, because the axes corresponding to the frame A and frame B are represented using the unit vectors XA, YA, ZA, and XB, YB, and ZB. So if you take a look case by case for each column, the first element is XB dot XA, right? The angle XB makes with XA. So since they are coincident with each other, the angle is actually 0, right? So cos 0 is basically 1. So the first element would be 1. And the second element for the second element of the first column would be XB dot YA, right? The angle XB makes with respect to the YA axis. From here, it is evident that both of them are orthogonal to each other, right? XB is coming out of plane. YA is actually lying inside the plane or within the plane. And the angle between XB and XA is 90 degrees. So cos 90 would become 0. So this column this element would be 0. And the same applies for the third element, xb dot za, because the angle between xb and za is again 90 degrees. So by extension, xb dot za is 0. Now, when we come to yb.xa, when we come to the second row, sorry, the second column, the first element corresponds to yb.xa, right? The angle the vector yb makes with respect to xa. So yb is still in plane and xa is out of plane. So cos, they are orthogonal to each other. So their dot product is obviously going to be 0. Now the second element would be yb.ya. So both of these vectors are within the plane, and you can see there is an angle, between yb and ya, right? So the dot product would be yb, ya cos 90. Sorry, cos theta, because the angle between them is cos theta. So the dot product extension would be cos theta, right? Now, if you consider the angle between the angle that yb makes with za, the angle between yb and za is 90 minus theta, right? So cos 90 minus theta is obviously sine theta. So that will be our third entry over here. And similarly, if you do with respect to the ZB axis, the angle ZB makes with respect to XA would be 90 degrees. So the dot product would be 0 because they are orthogonal to each other. The angle ZB makes with respect to YA, this would be minus theta, right? That would be minus sine theta, this angle. And the angle ZB makes with respect to ZA, this angle, that would be cos theta, right? So this is how you populate your rotation matrix. So in this example, we are only considering the rotation about the global x-axis, right? So this is how a rotation, a pure rotation about x-axis would look like. This is how you represent a pure rotation about x-axis. So in a similar manner, you can also populate the rotation matrix with respect to the y-axis. So now the rotation matrix change like this, right? So the second column, element 2, 2 would be 1, and all the other elements in the second row and second column would be 0. But these elements would be cos theta, sine theta, minus sine theta, and cos theta. If you're talking about pure rotation about y-axis. And in similar case, this is a pure rotation about z-axis. So the third element, the 3, 3 element of the rotation matrix would be 1, and the third, all the other elements of the third row and the third column would be 0. And the other elements would be populated like so: cos theta, minus sine theta, and cos theta. But then again, the general principle remains the same. Once you know how to populate these entries, based on the unit vectors, you can, for any compound rotations, you can actually do that. It does not necessarily have to be a pure. It does not necessarily have to be a pure rotation about x, y, or z axis. It can be a combination of, any of these cases. All right. Now, if you have two frames with same orientation, how do you represent the position of the second frame with respect to the first frame? Right. So in this example, we consider the description of the mapping between two coordinates frames when their orientations are exactly identical. So here you can actually see two frames. The first frame is frame A with XA axis pointing outward, YA and ZA axis in plane. And you have a second frame called frame B, here, if you compare both of these frames, you can actually see that their relative orientation is exactly identical. XA and XB axes are parallel, YA and YB axes are parallel, ZA and ZB axes are parallel. Now, if you want to represent, a point that is expressed in frame B, how would you represent the same point in frame A, right? Because one typical example I can tell you is that if you have two links of a robot like so, maybe two connected links like this with a joint. So I label this as link 1, I label this as link 2. I have a frame of reference attached to the first link. Maybe I'll call this as maybe y-axis, y1 axis. This could be x1 axis, and this could be z1 axis. And for the second link, you can have x2.
So,
Yes.
two frame, does it mean parallel manipulator?
Are you talking about, are we going to cover parallel manipulators in this course?
Because it is two frame.
Are you asking a question? What is I?
Yes, it is two frame. Does it mean that it is parallel manipulator, or it is still a normal one?
It can be any manipulator. The reason we are using frame of reference is to communicate the position and orientation between two rigid bodies. So rigid bodies can be part of serial robot or parallel robot, right?
Okay, sir.
If you want to specify the position of one rigid body with respect to another rigid body, you can do so by the use of frames. You are basically representing a rigid body by frames.
Okay, sir.
That's why we are using frames. So in this example, the relevance of this problem, I'm just trying to explain. Right? So you can consider these two rigid bodies as part of a robot, right? And we can represent these rigid bodies using the frame of references, right? So for example, if you have a point, maybe this point Q attached to the second frame, right? So by default, you know the position of this point Q, right, with respect to frame 2, because this frame 2 is always attached to the second link. So as the second link moves or rotates or translates, the frame 2 will also move along with the second, with the second body. So if you want to know, if you know the point of, if you know the coordinates of this point Q with respect to frame 2, how would you identify the position of this frame Q, point Q, with respect to frame 1? Right? Maybe this is like a very important point. Maybe this is the location of a sensor, right? But you for some reason you want to know the location of the sensor with respect to this frame, the frame of the first frame. Or maybe you have a frame like this, at the bottom, attached to the ground. So ground is where the human observers are actually standing, right? So if you want to know the position of this sensor with respect to the ground, first you have to back propagate the information from the point through all the frames, and eventually it will reach to the ground fixed frame. So in this example, we are trying to figure out the position of a point Q that is already expressed, that is already known, because this is always a fixed vector. This position of vector Q, the position vector of vector Q with respect to B is always going to be fixed. So if you know this vector, what would be the position of Q with respect to frame A? Right? That is given by this vector addition expression, right? So this basically say that the position of vector q with respect to A is nothing but position vector of B with respect to A plus position vector of Q with respect to B. So this is nothing but a vector addition, right? So sum of this vector plus this vector is this vector, just a vector addition. So this is only applicable when the two frames are having the same orientation, right? XA and XB are parallel, YA and YB are parallel, ZA and ZB are parallel. This is a very simple case. But if you take a look at a case where there is a orientation difference, between frame B and frame A, you have to bring in the rotation matrices into account. So one simple case is here, mapping involving rotated matrix. So for the time being, we consider the distance between frame B and frame A as 0. You can consider this distance to be 0. But I have separated these two frames just for clarity. So one example is that if you know the point Q with respect to frame B, what will be the coordinates of point Q with respect to frame A? So that is addressed by this equation, right? So we already know the position of Q with respect to B. We want to know the position vector of Q with respect to A. So we do so by pre-multiplying the position vector of Q with respect to B with a rotation matrix that specifies the rotation of B with respect to A. Right? This is how we mapping that we have to follow when rotated frames are involved. Maybe I'll give a very brief example, right? Consider the coordinates of point Q to be just 2 units in the YB axis, right? So maybe I'll give a small example like this. So this is ZB, this is YB, and XB is out of plane. So I'm just representing it with the dotted lines because in reality we won't be able to see that because it's coming out of plane. So this point Q is 0, 2, 0, right? 2 units with respect to the YB axis. But our fixed frame is something like this. ZA, you have YA like this, and XA is out of plane, like so. Right? So if the position vector of, I'll call this as Q, if the position vector of Q with respect to B is 0, 2, 0, what is the position vector of Q with respect to A? You can actually consider this distance to be 0 because we are only considering the rotation. Just ignore the relative distance between them as 0. So if you know the relative position of point Q with respect to B, in order to find the relative position of Q with respect to A, first you have to find out the orientation or the rotation matrix corresponding to the relative orientation of frame B with respect to frame A. Right? So we can again use that direction cosine orientation matrix representation. So to represent the orientation between B and A, you can have this rotation matrix as it will be XB dot XA xb dot ya, you have xb dot za, that will be the first column. Second column would be yb dot xa, yb dot ya, and yb dot za, and the third column would be zb dot za, zb dot ya, and zb dot za. So if you consider the angle xb makes with respect to xa, you can actually see that both of them are parallel to each other, right? So since they are parallel, xb dot xa is going to be 1. And the second entry of the first column, xb is perpendicular to ya. So that term is going to be 0. And in the same line, xb is perpendicular to za, so that is also 0. And now coming on to the second column, yb is actually parallel to za, right? yb is parallel to za. So you can actually see this term, yb dot za, is the only term that is going to be 1. All the other term are going to be 0. So it'd be like 0, 0, 1, right? Because yb and xa are perpendicular, so that is 0. yb and ya are perpendicular, so that is also 0. yb and za are parallel, so that makes it 1. And coming on to the third column, zb, the first element is zb and za. So zb and za are perpendicular, so that is 0. Now the second term is zb and ya. You can see that they are parallel, but they are in the opposite direction. So the direction cosines or the dot product is going to be -1. And zb and za are again perpendicular, so that is going to be 0. So according to this relation, you have to pre-multiply the position vector of q with respect to b by using this rotation matrix. So you will get it as 0, 1, 0, 0, 0, 0, -1, 0, 1, 0. And you multiply that with our known position vector, that is 0, 2, 0. If you multiply this out, you will be getting it as 0, 0, 2, right? So the position vector of q with respect to a is 0, 0, 2, right? You can directly see it from this figure, right? If these two frames are coincident, and if there is a point that is 2 units along the yb axis, that same point is actually going to be 2 units along the za coordinate, right? Because za and yb are aligned. So if you are moving 2 units in the yb coordinate, that basically means that you are moving 2 units in the za coordinates. So from that rotation matrix equation, you are getting the same information, right? Position vector of q with respect to a is 0, 0, 2. So there is that. Now we'll see one more case where, if the position between frames B and A is not 0, what you have to do is you simply add this quantity with position vector of B with respect to A, like so, right? So if the position vector of Q with respect to B is known, and you are required to find out the position vector of Q with respect to A, this is nothing but a simple vector addition. You add this vector and you add this vector, you will get this big vector. But since this vector is represented with respect to the rotated frame B, we have to represent this quantity with respect to frame A, because all the vectors have to be represented in frame A. For that, we are using this rotation matrix. So we pre-multiply position vector of Q with respect to B with the rotation matrix position vector of B with respect to A, and then add it with this vector, right? Position vector of B with respect to E. So now all vectors, if you take the superscript, all the all the vectors are expressed with respect to the A frame of reference. Maybe if you simplify this, you will get this final relation. Position vector of Q with respect to A would be position vector of B with respect to A plus position vector of Q with respect to A, right? Where if you do this operation, you will get this vector, so that all vectors are represented with respect to the A frame of reference. So with this equation, you are basically communicating the relative orientation of frame B with respect to A, the relative position of frame B with respect to A, and position of any arbitrary point that is expressed with respect to frame B. So this is all you need to map, the position and orientation, or if you want to transmit information regarding positions and orientations, this is all you need, for a robotic manipulator. So, instead of writing it like separately, we write one term just for position and one term just for orientation. We can club all these information using a single 4x4 matrix. We call this as a transformation matrix. This is actually a 4x4 matrix. So basically, this is an operator which maps one frame to another in matrix form. For example, if you have a frame of reference like this is XA, this is YA, and this is ZA. And you have another frame of reference, maybe probably some far away with a different orientation, maybe XB, YB, and ZB. You can represent the relative orientation of frame B with respect to frame A, just the relative orientation, using this rotation matrix, right? And the positional information can be captured by this position vector, position vector of frame B with respect to frame A. And the final row would be nothing but 0, 0, 0, 1, right? So the rotation matrix is a 3x3 matrix. The position vector is a 3x1 vector. And the final row is nothing but 0, 0, 0, 1. So if you want to transmit, or if you want to convey the position and orientation of frame B with respect to frame A, you have to assemble a 4x4 matrix with the first 3x3 element to be a rotation matrix, and the 3x1 part to be the position between these two frames. And then the final row for all transformation matrix is going to be 0, 0, 0, 1. And if you want to find out the inverse transformation, right? If you want to find the transformation of frame A with respect to B, you have to take the inverse of this 4x4 matrix that is given by this expression, right? So the entire inverse can be decomposed using this expression. The inverse of the rotation matrix is the transpose, because the rotation matrix is basically an orthogonal matrix, orthonormal matrix. So its inverse is always going to be the transpose. And the inverse of this position vector is given like so. You have to pre-multiply the position vector with a rotation matrix with its transpose and a negative sign also. But just like in case of any transformation matrix, the final row is always going to be 0, 0, 0, 1. Right? And the proof of this is actually not that difficult. It's given in the lectures in NPTEL. If you want to have a look at the proof, you can do so. Or if you have any doubts regarding how you got this expression, you can let me know now. I can also show you, but since we have time limitations, I'll move on to the to the other topics. All right, so now we have one important question. Do we pre-multiply subsequent rotations, or do we post-multiply subsequent transformations? So, for example, if you have a rigid frame of reference like so, for example, I'll depict this as x1, y1, and z1, and there is also a mobile frame. If you consider the frame 1 to be a fixed frame, it's always going to be fixed to the ground. And there is a mobile frame. I'll call that mobile frame as frame 2. So the mobile frame is actually going to be rotated. So depending upon how you specify the mobile frame, you have to either pre-multiply the transformation matrix or you post-multiply the transformation matrix. So initially, you can consider the both of the frames to be coincident. So Z1 and Z2 are aligned, X1 and X2 are aligned, Y1 and Y2 are aligned. So if you are specifying the rotations, all the rotations or translations of frame 2 with respect to the fixed frame, so all the subsequent transformations will have to be pre-multiplied. But in case if you are specifying the rotations of the mobile frame with respect to the axis of the mobile frame itself, all the subsequent transformations will have to be post-multiplied. Right? We will see that in the subsequent examples. Right? For example, if you rotate about x-axis by an angle 90 degree, and if you rotate by y-axis by an angle 90 degree, you can get a different result based on what x and y-axis these are. If these are if the first rotation is about x-axis with respect to the fixed frame, that will be the first transformation, maybe r z 90. And if the subsequent rotation about the y-axis is defined on the fixed frame itself, you have to pre-multiply ry 90, right? But if the first rotation is about z-axis and the subsequent rotation is about the y-axis of the mobile frame or the rotated frame, you have to post-multiply ry 90. And obviously, since matrix multiplication is not commutative, these two results are going to be different. Right? Maybe I'll show one example. Maybe probably example 1. Example 1. This will be like rotations about fixed z plus rotation about fixed y. So we consider the rotation to be 90 degrees. So initially, you can consider the mobile and the fixed frame to be coincident. Z1 and Z2 are coincident, X1 and X2 are coincident, Y1 and Y2 are coincident. So in the first rotation, we are rotating 90 degrees with respect to Z-axis. So X1, Y1 axis would remain the same, but the second mobile frame would look something like this. If you are rotating 90 degrees with respect to Z-axis, your Y-axis would be now, Y2 axis would be aligned like this. X2 axis would now go up, and Z2 axis is going to be perpendicular to the plane. Now, the second step is rotation about the fixed y-axis. Now, after we have achieved this, we have to rotate about the fixed y-axis. So if you are rotating this frame with respect to the fixed y-axis, the second subsequent transformation would be something like this. X2 axis is going to go out of plane. Z1 axis is coming like this. So Z2 axis, and Y2 axis. Sorry, I think, yeah, if you are rotating about global fixed y-axis, this Z2 axis is going to be similar. So that is X2 actually. X2 is going to stay the same. Y2 is now coming out of plane, and Z2 is going like this. Right? So this is the first step. I'll write it like this. Rotation about Z1 by an amount 90 degree. And the second step is rotation about Y1 about 90 degree. So initially we begin with 2 frames coincident. Now we ended up with X2 vertical, Y2 in this direction, and Z2 in this direction. And to achieve this final configuration with respect to the initial configuration, you have to pre-multiply. R Z 90, R Y 190. We pre-multiply when all the transformations are involving with respect to the fixed frame. But instead of representing everything with respect to the fixed frame, we can represent the rotations with respect to the current frame. Whatever frame we have, the subsequent rotations will be represented with respect to the current frame. In that regard, we post-multiply, to get the correct transformation. We'll, see that as we are doing some problems. Okay, so now we move on to some sample tutorial questions. If you have any doubts, please feel. Yeah.
Sir, can you explain what is pre-multiply and post-multiply, sir? I got it some confusion, sir. What is pre-multiplication?
Pre-multiplication is, if you have 2 subsequent,
sir, that I understood, sir. So in XYZ axis, in the extreme right, we will write Z, then Y, then X.
Yes.
So that is pre-multiplication, sir.
It depends upon how you specify the subsequent transformations. If all the subsequent transformations are represented with respect to the fixed frame of reference, you have to pre-multiply, right? So for example, if your course of action is rotate about the fixed frame Z1 axis by 90 degrees, and the second transformation is rotate about maybe Y1 axis about 30 degrees, and the third specification is rotate about maybe X1 axis by maybe 50 degrees.
Okay, sir.
So in this case, initially, the fixed frame and the mobile frame are coincident. Like there is no change. So maybe you can represent that with an identity matrix, maybe an identity matrix I3 by 3. It's because all of them are oriented. Now, the second step is you are rotating about Z1 axis by an angle 90 degrees.
Yes, sir.
So since we are rotating, or since we are specifying the rotations with respect to the fixed frame, notice all the subscripts being 1. 1 basically denote the fixed frame.
Okay, sir.
If that is the case, we have to pre-multiply the subsequent, subsequent transformations.
Right, sir. So first extreme right, we will write Z1, then Y1, then X1.
Yeah, so it'll be like this. So it'll be like R Z 90.
Yes, sir.
Then again you have to pre-multiply with R Y 90. Then again you have to multiply R X 90.
Yes, sir. Yes, sir.
So all the subsequent transformations goes to the left.
Okay, that is pre-multiply. Okay, sir.
Pre-multiplication.
Okay. Yes, sir. Thank you, sir. Thank you.
Yeah. So the same goes for post-multiplication, right? If your order is something like this, you rotate about Z1 axis by 90 degrees, you rotate about Y1 axis about 30 degrees, but for the final step, you rotate about the moving frame, about Z2 by 50 degrees.
Yes,
so
sir.
in
That
that
term
case,
is little confusing for me, sir. Now it's okay, sir.
Okay. So just to finish it off, in this instance, it will be something like this. Initially, you will begin with the rotation matrix, rotation about Z1 by an angle 90 degrees. And the second transformation is again with respect to the fixed axis. So now we pre-multiply again Ry with respect to 30. But now the rotation about x-axis is specified with respect to the moving frame. So since this is moving frame, we post-multiply. So now Rz will come here, this side, Rx to 50 degrees, right? So whenever the transformation is represented with respect to the moving frame, we post-multiply. Whenever the transformation is represented with respect to the fixed frame, we pre-multiply. So that is basically the difference. All right, so hopefully this will be more clear as we solve some sample questions. So we'll solve 10 questions. It'll probably only take less than a minute, to solve these questions. All right, so the first question is, in effector, any sort of effector, if the effect on the environment causes the motion of the effector itself, it is called, so out of all these options, what would be the most appropriate choice? So like at the beginning, we have discussed there are two types of effectors. One is called manipulators, and the second one is called mobile robots.
Locomotion.
If anyone knows the answer, you can let me know. You can use your microphone to call out the answers.
Locomotion.
Exactly, it's correct. The answer is locomotion. Right? If the effect causes the motion of the device itself, that is called locomotion. But in case of manipulation, the effect causes the motion of the objects, around it. So yeah, that is indeed the correct answer. The correct kind of effector that we are looking for in this question is locomotion. Now we move on to the second question. So a kind of robot or a dash robot manipulator has more than one loop, right? End effector is connected with multiple serial chains. So what sort of robot or what sort of manipulator has more than one loop or has more than one serial chains?
Serial robot.
Is it serial robot? Or is it parallel robot?
Parallel robot.
Yes, exactly. It is parallel robot. Right? Because in case of a serial robot is actually made of links connected, one after the other, like so, using some joints. Right? You call each of these rigid bodies as links, Links. Right? But in case of a parallel robot, like so, you have a top platform. Maybe this could be a flight simulation cockpit. And you have a ground over here. So in case of a parallel robot, you are connecting the top platform using several serial chains. So this could be one chain. This could be another chain. This could be another chain. So this is a schematic representation of a parallel robot. So in case of a parallel robot, again, you have links. These individual rigid bodies are again called links. These are all links. right? But then we call each of these serial chains as legs or limbs. Collectively, this entire assembly, we call it as leg or limbs, right? And as you can see, there are multiple closed loops. There is a closed loop like this. There is also another closed loop like this. But in serial chain, there is no closed loop. Between the base or between the ground and the end effector, you only have a single serial chain. There is no closed loop. But in a parallel robot, there are multiple such closed loops. So the correct answer for the robot manipulator that has more than one loop, or if the end effector is connected with multiple serial chains, such kind of robots are called parallel robots. So I hope that is clear. The correct answer is indeed parallel or closed chain robots. We can call serial robots as serial robots or open chain robots, but those with multiple legs or multiple limbs, we call them as parallel or closed chain manipulators. Okay, now we move on to a numerical question. Find the rotation matrix C with respect to A. The following details are given for numerical calculations. So the question basically gives you two rotation metrics, rotation of B with respect to A and rotation of C with respect to B. Right? Rotation matrix of B with respect to A is given as 0, -1, 0, 1, 0, 0, and 0, 0, 1. And rotation matrix of C with respect to B is given as 1, 0, 0, 0, 0, -1, and 0, 1, 0. And you are asked to find out, the question is asking you to find out the rotation matrix of C with respect to A. This is what you are supposed to find out.
These? You
can multiply this, exactly. So A with respect to B.
Multiply the matrices.
Multiply by B, C, multiplying this would give you the rotation matrix of C with respect to A. Simply multiply it out like so. Right? So if you do that, if you multiply it out, -0, -1, 0, 1, 0, 0, 0, 0, 1. And then the other one is 1, 0, 0, 0, 0, -1, 0, 1, 0. So if you multiply this out, you will get the answer as, I think, 0, 0, 1. Then you will get 1, 0, 0. Then it will be 0. Is it 0, 0? Sorry. It will be, 0, 1, 0. Just simply multiplying this out. Right? So it basically means that you have a B frame.
You are not audible.
Am I audible now? Hello? Am I audible now?
Yes, sir.
There's no problem.
Okay. So the question basically means you have a matrix, you have a frame A, you have a frame B, and you have a frame C. And orientation of frame B with respect to A is known. Orientation of frame C with respect to C is also known. You are asked to find out the orientation of C with respect to A. That is done by simultaneously multiplying the individual rotation matrices like so. So the answer is indeed option A in that regard. That is indeed option A. And moving on to question 4, you are given a rotation matrix B with respect to A. you are asked to find out the inverse of the transformation, the matrix inverse. Again, this is a straightforward problem. If you have a matrix B with respect to A, the inverse would be the transpose of that matrix.
So this is because it's orthonormal, right?
Yes, exactly. It's because it's orthonormal. Because if option would be
A. First option.
Yes, correct. Because for any rotation matrix, not for this particular example, if you take the norm of this unit vector, that is going to be 1. If you take the norm of this unit vector, that is going to be 1. And if you take the norm of this column vector, that is also going to be 1. So this is like an orthonormal vector, because the norm of all the columns are going to be 1. And if you take the dot product of any two columns, those are going to be 0. So they are orthogonal to each other because their dot products are 0 and their individual norms is unity. So they are normal. So it's like an orthonormal matrix. And for any orthonormal matrix, their inverse is also their transpose. So that is indeed the correct answer. Now moving on to question 5. Now we are dealing with a full-fledged transformation matrix problem. So there are 3 frames, A, B, C. So the transformation of B with respect to A is given as 1, 0, 0, 0, 0, minus 1, 0, 0, 0, 0, 1, 0, and you have 5, 4, 0, 1. And the transformation of C with respect to A is also given as 0, 1, 0, 0, 1, 0, 0, 0, 0, 0, minus 1, 0, then 10, 5, 0, 1. You are asked to find out the transformation of C with respect to B. This is what you are supposed to find out.
So from this, we can get the rotation matrices of A with B with respect to A and C with respect to
A. You want to extract rotation matrices? Okay,
yes.
then?
Then we can multiply to get B with respect to C. Okay, no, because it's A respect to B and A respect to C.
Yes.
So we can take the transpose, I suppose.
No, the ultimate thing why we are using this transformation matrix, because the first 3 by 3 is a rotation matrix, and this part would be this part is actually going to be the position vector, and this is always going to be 0, 0, 0, 1. The reason why we are using this representation, using transformation matrix, is that we can treat positions and orientations simultaneously together. So just like how we did the previous problem on rotation matrices, you can actually compound the transformations like so. So transformation of B with respect to A. Sorry, the question asks. Sorry, you have 3 frames actually. Transformation of C with respect to A would be transformation of B with respect to A multiplied by transformation of C with respect to B. I hope we can all agree on this, right? You are given, transformation matrices. Each of these transformation matrices are of interest in this problem. This one is given in the question. Transformation of B with respect to A is given in the question. Transformation of C with respect to A is also given in the question. These 2 transformation matrices are given. You are asked to find out this one, transformation of B with respect to C. This is what you are asked to find out.
Yes, so as I was saying, like my theory would be to take the inverse of transformation A with respect A and B. But since it will be difficult to take the inverse, we will just take the transform of the rotational matrix.
Okay, then what about the positions then?
That is one part I'm not sure.
Okay, so if you you can still take the inverse, right? Why not? Because we have already discussed if you have a transformation matrix, transformation of what do we want? What inverse do we have to take in this question? I think we have to take the inverse of, yeah, this is what we have to take. Transformation of B with respect to A, you can represent it using a rotation matrix, rotation of B with respect to A, position matrix of B with respect to A, then the final row would be 0, 0, 0, 1.
Yes, sir.
If you want to take the inverse, transformation of B with respect to A inverse, or transformation of A with respect to B, both are the same. This is nothing but the inverse would be given by the rotation matrix of B with respect to A transpose. Then you have minus rotation matrix of B with respect to A transpose multiplied by position vector of B with respect to A. Then you have this final row as 0, 0, 0, 1. This is what you have to do to find out the inverse. Right? If you want to find out the inverse of a matrix, I mean, if you have a calculator, you can simply plug in this equation and take the inverse of it. That is one way. If your calculator supports inverse of a 4x4 matrix, you can simply if you can simply input this matrix and try to find out the inverse. Or if you want to do manually, this is how you have to do this individually. So again, it's not a complex problem. If you can basically know what is going to be this one, right? Because this is nothing but the transpose of this matrix, transform of this rotation matrix. And this part, you multiply the transpose of the rotation matrix with the previous rotation matrix, like so. And then you multiply the final column would be 0, 0, 0, 1. That is how the inverse is going to be. Right? Maybe I'll show that example. Maybe I can work it out here itself. How would it look like? So I'm going to write transformation of the inverse of the transformation of B with respect to A inverse as probably how do I? Yeah, it will be like rotation matrix of B with respect to A transpose, negative of rotation matrix of B with respect to A transpose, position vector of B with respect to A, then 0, 0, 0, 1. So this ARB transpose is, you can simply take the transpose of this part. That is going to be 1, 0, 0. Then it is going to be 0, minus 1, 0. Then 0, 0, 1. Then if you multiply with the position vector, this part, 5, 4, 0. There is also a negative over here. You will be getting, it'll be like 5, 5, negative 4, 0. And if you account for the negative sign, it will be like negative 5 plus 4 and 0. So again, the transformation, the inverse transformation matrix would look something like this: 1, 0, 0, 0, minus 1, 0, then 0, 0, 1. Then the final column would be -5, 4, 0. Then the final row would be 0, 0, 0, 1. And now once you have this inverse transformation, what are you going to do? Do you pre-multiply or do you post-multiply? That is the question. I'll again write that relation. Transformation of C with respect to A is transformation of B with respect to A multiplied by transformation of C with respect to B. So you are asked to find out, this would be your unknown. This is what you are supposed to find out. And we have already found out the inverse of this transformation. So what are you going to do with this inverse to find out this part? Do you, pre-multiply this, transformation of C with respect to A with the inverse, or do you post-multiply? Do you multiply it over here or do you multiply it over here? That is the question. Any answers regarding that? So what is the correct answer? So
The inverse will go to the left-hand side.
yeah, so you are saying this would be the correct answer?
Maybe yes.
Yes, sir. Yes, sir.
Yes, sir.
Or should I do something like this? Which would be the correct one?
So the first one.
Yeah, the first one is actually correct. Because, in the left-hand side, if you multiply this side with the inverse of this quantity, those two terms is going to be an identity matrix. So the only term that is going to remain is here, this term. So in that regard, you also have to pre-multiply this term with the inverse. That is the correct term. So in that regard, you already have this inverse transformation and you multiply that with transformation of C with respect to A. And from that question, it is 0, 1, 0, 10, 1, 0, 0, 5, 0, 0, minus 1, 0, and 0, 0, 0, 1. And if you multiply this out, I believe you will get option A as the answer. That is 0, 1, 0, 5, minus 1, 0, 0, minus 1, 0, 0, minus 1, 0, and the final column is 0, 0, 0, 1. This would be transformation of C with respect to B, which would be option 1. Right? Again, these are fairly simple concepts to understand. The important thing that you need to remember is how to assemble this rotation matrix. That is one important aspect. And another important aspect is whether you pre-multiply or post-multiply, depending on how the orientation is specified. That is the only concern that we have. Everything else, like once you practice more problems, similar problems, everything will be intuitive, actually. Don't really have to think. Yeah, so option A is indeed the correct answer. Moving on to question 6. If a moving frame is initially coincident with a fixed frame, is rotated 90 degrees clockwise about the fixed y-axis, translated 5 units about the fixed x-axis, and rotated 90 degree clockwise about the fixed x-axis, then what is the final pose of the moving platform? So I think it has 3 parts. First, we have to, rotate 90 degrees clockwise with respect to the fixed y-axis. Then we translate 5 units about the fixed x-axis and rotate 90 degree clockwise about the fixed x-axis. So like we can solve this problem graphically or using the transformation matrices. Either ways, we should get the same answers. So maybe I'll depict the graphical way first. So maybe I'll consider the initial frame like so. Y-axis is aligned like this. X-axis is aligned like this. And Z-axis is out of plane, right? It is coming perpendicular to the plane of this page. So I'll depict this as the Z-axis. And as before, I'll consider the suffix or the subscript 1 as the fixed axis. Z1, X1, and Y1. Maybe I'll denote it here. Frame 1 denotes the fixed frame of reference. So the first transformation is, the frame is rotated 90 degrees clockwise about the fixed y-axis, right? So the vertical axis is the y-axis. And if you are rotating about the y-axis in the clockwise sense, like so. So clockwise sense is that you have to curl your arm, you have to curl your right arm in a way that your thumb would be pointing in the negative y-axis, clockwise rotation, right? So if you are rotating clockwise about the y1 axis, what is the new orientation of the moving frame, right? So y-axis is going to be the same. I'll represent frame 2 as the mobile frame. So after the first set of transformation, y2 would still remain parallel to y1, right? And since we are rotating clockwise, this x2 would now be rotated perpendicular to the board. So x2 would be like perpendicular to the board. And z2, so this z2 would be rotated perpendicular, would be in this direction, parallel to the board, but along this direction. So z2 would look something like this. Right? Initially, frames 1 and 2 are coincident, but now, since we are rotating about the y1 axis, this is the new orientation of z2. Now, the question also says, after we have rotated 90 degrees clockwise about the fixed y-axis, the frame is translated 5 units about the fixed x-axis. So the distance between the two frames, 2 and 1, is 5 units about the x-axis. So I'll mark this distance along the x-axis as 5 units, right? And now the final transformation is and rotated 90 degrees clockwise about the fixed x-axis, right? So now you rotate this mobile frame with respect to the fixed x-axis in the clockwise sense. So again, the clockwise sense is if you try to curl your right arm in such a way that your thumb is actually pointing in the negative x-axis, that is the clockwise rotation with respect to x-axis. How would this frame look like? How would this frame now change? So if you are rotating about this x1 axis, since x1 and z2 are aligned, the new orientation of z2 is still going to be same. This is z2. And now this y2 is actually going out of plane because we are rotating about x1 axis. It's going out of plane. So y2 is going to look like this.
Excuse me, sir.
Yes.
Sir, in the question it was said that translated 5 units about the fixed x-axis.
Yes, correct.
But from the figure, is it not that you have taken distance from the moving x-axis?
No,
5 units, x2.
This is the fixed x-axis, right? This is
X1,
the fixed
X1
axis.
is yes, sir.
X1 is the fixed. So from along X1, this is the origin of the fixed frame of reference. So we are displacing frame 2 along X1 by 5 units. So the
statement about fixed axis means in the direction of x-axis.
In the direction of X1 axis.
Yes, sir. Meaning like about means in the direction.
In the direction, yes.
Okay.
It should be along probably. Instead of about, it should have been along.
That was my doubt because about seems kind of tricky to understand.
Yeah, so it should be along. That probably makes more sense.
Yes, sir.
Yeah.
Okay. And the last rotation was 90 degree about the fixed x-axis.
Yes. Rotation is about fixed x-axis.
Okay.
Right? You have to rotate this mobile frame with respect to the fixed x-axis. Now, since Z2 and Z1 are aligned, if you are rotating about X1 axis, Z2 is still going to be the same, right? If you are rotating like this, Z2 is going to be the same. And Y2, earlier it was vertically up, now it's going out of plane, like so. And X2, earlier it was out of plane, but now it'll basically come up, like so. X2 would be like this.
Excuse me, sir.
Yes.
I have another doubt. It is written that 90 degree clockwise about fixed x-axis. So when we are fixing in the direction of x1, won't we rotate the opposite side? Like won't y2 come down on the side of x2? Because it is clockwise in the direction of x-axis.
Clockwise would be like this, right? This is clockwise sense. Like if you are looking perpendicular to the, x1, y1 plane, if you are rotating clockwise with respect to x1 axis, earlier y1 was like this. When you rotate clockwise like so, y1 would go like this. And if you're rotating clockwise, Z1 was out of plane, it would come vertically up. Isn't that so?
I still don't understand.
Huh?
I still don't understand.
All right. You are having doubt about the final transformation, right?
Yes, sir. Because in my point of view, we will rotate the x-axis when we are facing towards it. Like I am facing towards right, so I will rotate right, not left. That's what I'm thinking.
Okay, so do you agree that Z2 will remain the same orientation?
Yes, Z2 will remain the same because X1 and Z2 are on the same axis.
Okay, so I am now going to depict an orthogonal view of this X2 and Y2 plane, right? So yes, if I'm looking along the direction of X1, right? Along the direction of X1, this would be X2 and this would be Y2, right? And clockwise rotation about X1 would be this direction, right? Yes, because X1 is out of plane. X1 is actually out of plane. The X1 axis is out of plane. You are looking along X1 axis. So the plane perpendicular to X1 axis would be X2 and Y2. So in this graphic, I'm actually looking perpendicular to X1 axis, so that X2 axis is like this, Y2 axis is vertically up.
Okay, so when we are basically transforming it, we are seeing it from the origin of the moving plane, not the fixed plane.
Yes, because you are rotating the moving plane, right? You are moving the rotating plane with respect to X1 axis.
Okay, see what I was originally doing was I was sitting on the origin of plane 1, or on the origin of axis of 1. So and from that, I think you would understand why I was saying that it would move in the opposite direction.
You are looking from the origin of plane 1?
Yes, that's why I was thinking about that.
Okay, understood. Okay. Okay, so now
I will remember to always look from the origin of the moving, right?
You have to look the origin of the moving along the direction of the rotation.
Got it.
Perpendicular to the direction of rotation. So since you are rotating with respect to x1 axis, the y2 axis now will move out of plane, and z2 axis will be the same because x1 and z2 are aligned, and x2 axis, earlier it was out of plane, now it will come straight up. So this is your final transformation, right? So the original earlier transformation was this. I'll just bring it down just for comparison. So this was the original Z1 axis. This was the original X1 axis. And this was the original Y1 axis. And the distance between the two frames is still 5 units. So if this is the final transformation, or if this is the final pose, and if this is the original pose, how will you assemble the transformation matrix? Because the transformation matrix will compose of a 3x3 rotation matrix. Then you have a 3x1 transformation matrix, and then you have the 0, 0, 0, 1. So in that regard, how will you assemble this transformation matrix? I can do so by first comparing the angle x2 makes with respect to x1, y1, and z1. So now, as you can see, x2 is now parallel to y1, right? So the first column would be 0, 1, 0, right? Because x2 is parallel to y1. x2 and x1 are perpendicular, so their dot product is going to be 0, which is this one. x2 and z1 are perpendicular, so their dot product is 0, that is this one. But x2 and y1 are parallel, so their dot product is 1. Now the second column, we do the same for y2 axis. So now you can see y2 axis is parallel to z1, but in the opposite direction. y2 is going out of plane, away from us, but z1 is also out of plane, but coming towards us. So now y2 would be now 0, 0, -1. I hope that is clear, because for other cases, y2 and x1 are perpendicular. y2 and y1 are again perpendicular. y2 and z1 are parallel, so but in the opposite direction. And same for z2 with respect to x1, y1, and z1. And now from here you can see z2 and x1 are parallel, but again in the opposite directions. So that becomes -1, 0, 0. So we are done with the rotation matrix part, right? Now what remains is the translation in vector. So that basically is just 5 units. The position vector of frame 2 with respect to frame 1 is just 5 units along x1. So we can simply say this as 5, 0, 0, and the final row would be 0, 0, 0, 1. This would be the transformation matrix of frame 2 with respect to frame 1. This is how you can do this graphically, or if you want to do that using the rotation matrix, using pre-multiply or post-multiply, you can do so like this. So the first transformation matrix would be the transformation matrix. Maybe I'll just represent it with transformation, but this is a pure rotation about y-axis in the clockwise direction. So clockwise direction, we always give a minus 90 degrees. And counterclockwise, we always give a positive sign. And the next transformation, since it is with respect to the fixed frame of reference, we pre-multiply. So the second transformation is translation about x-axis, 5 units. And the final transformation is again with respect to the fixed x-axis. So again, we pre-multiply. Transformation of, it's rotation about x-axis, again in the clockwise 90 degree. So we pre-multiply. So all these are pre-multiplied. So this elementary transformation matrix would look something like this. Earlier, it was pure rotation. So if you can recall from the earlier case, pure rotation about y-axis would correspond to a rotation matrix like this, 0, 0. This is cos minus 90, sine minus 90, then minus sine 90, cos 90. Then all the others are 0. And since this is pure rotation, the translations are all going to be 0. And the final row is going to be 1. So this corresponds to the pure rotation, transformation matrix corresponding to the pure rotation about y-axis. Then we pre-multiply this with the pure translation about the x-axis. So in case of a pure translation, the rotation matrix is going to be an identity matrix. But we are translating 5 units about the x-axis. So that becomes 5, 0, 0, and bottom row is 0, 0, 0, 1. And finally, we again pre-multiply this with the pure rotation about x-axis. So the pure rotation about x-axis would correspond to cos of minus 90 minus sine of, maybe I don't have to fill it again. Yeah, but the I'll just write it as Rx minus 90, then the position vector, that is going to be 0, all zeros, because it's a pure rotation. And the final row is going to be 0, 0, 0, 1. And if you multiply this throughout, you will still get the same answer.
So
but
could
here
you
yeah.
actually write the matrix, because I'm a bit confused how to write it.
Which
But
matrix?
the final one, transformation of x-axis 90 degrees.
Transformation of x-axis with respect to 90 degrees would look something like this. Cos of minus 90, because we are rotating clockwise, so that's why we have this minus 90. Then we have minus sine of minus 90. Okay, I think I made a mistake. I think it's like 1, 0, 0, 0, 0. Then you have cos minus 90 minus sine of minus 90. Then sine of minus 90, cos of minus 90. Then, since it's a pure rotation, the translational part is actually all 0, then 0, 0, 0, 1. This corresponds to the rotation about x-axis. Clockwise rotation about x-axis with the angle 90 degrees.
How do we know where to put?
How do you know where to put these terms, sir? Cos 90 as 90?
Yes, these only.
Okay,
like
so
the y-axis one we put 0, 0, 0, but here we put 1, 0, 0, and the things are different.
We have actually explained that in one of the earlier slides. I can go back. So, in case of pure rotation about x-axis, you can actually see that there are there are two axes, xa and xb. So you can consider xa to be the fixed and xb to be the moving frame. So if I'm rotating about xa axis, xa and xb are going to be parallel because initially they were coincident.
Okay.
But now yb and ya are going to be at an angle theta, right? Because you're rotating by an angle theta with respect to xa axis. So initially YB was coincident with YA, but now YB is at an angle theta from YA. And similarly, ZB will also be an angle theta from ZA. I hope that is clear. That part is clear.
Yes.
Okay. So how are we going to assemble this rotation matrix? We assemble this rotation matrix by comparing the dot products of XB with respect to XA, YA, and ZA axis. So the first column, if you see the first column, it is basically the dot product of XB with XA, YA, and ZA. Right? The first column is XB.XA, XB.YA, XB.ZA. And the second column would be the dot product YB mixed with XA, YA, and ZA. Right? So the first element would be YB.XA, YB.YA, YB.ZA. And the third column would be the dot product of ZB with respect to XA, YA, and ZA.
Got it, sir.
Right? So in the first case, the angle dot product of XB and XA is going to be 1 because the angle between XB and XA are 0. So XB, XA cos 0 is going to be 1 because XB and XA are basically unit vectors and cos 0 is 1. So that's how you are getting this one. Right?
Got it, sir.
And the remaining two elements are going to be 0 because XB is perpendicular to YA and XB is perpendicular to ZA. So both of these are zeros. And for the second column, it says the dot product of YB with respect to XA. Right? So if you consider YB and XA, they are again orthogonal, right? Because XA is coming out of plane, YB is in plane. So their angle is, they are basically orthogonal. So YB.YA is 0, right? Now that is this first element. Now what about the second element? Second element is YB.YA, the cos product dot product of YB and YB. So now you can see, since we are rotating about XA axis by an amount theta or by an angle theta, the angle between YB and YA is theta. So their dot product would be YB, YA cos theta. And since the magnitude is 1 for YB and YA, this essentially becomes cos theta. So YB.YA is cos theta. Right? And now for the third column, YB.ZA, that is actually going to be the angle that YB makes with ZA. So you can see that YB dot ZA would be YB ZA cos 90 minus theta, because the angle between YB and ZA is 90 minus theta. So this is nothing but sine theta, right? That is how we are getting this element, the third element. YB dot ZA is sine theta.
And similarly for the others, yes.
Similarly for the others, yes. Right. So that is how we are solving. We have solved the problems. Okay, so I think in that regard, we have covered two cases. One, we have covered this case graphically, and the other we have covered it using the rotation matrices. That is question 6, and the correct answer is indeed option A. And now I believe there are 4 more simple questions, actually, MCQ questions. Dash is a set of points where the manipulator can reach with any arbitrary location of the end effector.
Dexterous workplace.
That is dexterous workplace. We have discussed this previously. And for question 8, it's a true or false question. If the mobile frame is to be rotated by an angle theta about the kth unit vector of the fixed frame, then post multiply with rotation matrix. Is it true or false? If the current frame is rotated, or if it is transformed with respect to the fixed frame, do we pre-multiply or post-multiply? I'll just write it over here so that we can remember it.
Sir, fixed frame means
it should be post-multiply.
pre-multiply, sir.
It's mobile
Post-multiply.
frame, I think it should be post-multiply.
Yes.
I think post-multiplied is correct.
Okay. So transformation about mobile frame, we post-multiply, and transformation about fixed frame, we pre-multiply. But in the question, what does it say? Yeah. If the mobile frame is rotated by an angle about the kth unit vector of the fixed frame, then we post-multiply. So is it true or false?
False.
It's false. Correct. All right. Now, the second last question for this session. If the operational space variables are given and the geometrical variables are known, then finding the configuration space variables is known as. Is it inverse kinematics? Is it forward kinematics? I mean, like we would be using the other terminology actually. Instead of operational space, we would prefer to use the task space variables terminology.
Inverse.
Yeah, I got one answer as inverse.
Forward.
No. It's inverse.
Inverse.
It's inverse.
Then finding the configuration.
We are basically given the x and y coordinates.
Yes, correct. Okay, so given x and y coordinates, you are asked to find out the joint variables, theta 1, theta 2, etc. So what do we call these sort of problems actually? Given the task space variables, we are asked
Inverse
to find out
kinematics.
That's indeed inverse kinematics. That's correct.
Basically moving the robotic arm.
Exactly. If you want to move the robotic arm to a desired position, you have to find out what inputs that you have to give to the motors. So that is given by the inverse kinematics. So in the next week, we will see how to solve inverse kinematics problems. So the correct answer is indeed inverse kinematics. Now moving on to the final question, like this is a simple question. Rotation metrics corresponding to 30-degree rotation about the positive y-axis. Which of the options is correct? I mean, we can all agree that it has to be either this, or this, right? Because rotation about y-axis would have, the 2 element to be 1, and all the other elements in the rows and columns would be 0.
Third one.
Third one. This one, huh? Actually, no. The answer is actually the second one, right? So I'll just write it down. Rx would be 1, 0, 0, 0, 0. This will be cos theta. This is minus sine theta. This is sine theta. This is cos theta.
Okay.
Ry would be
Y sine will comes under down.
Yeah, the negative comes under the down. So it'll be like cos theta, sine theta, minus sine theta, and cos theta. And Rx would be cos theta, minus sine theta, then sine theta, cos theta, then 0, 0, 1, 0, 0. So only thing to be taken care of is when you have this y, the negative sign of the sign will come to the other side. That's the only thing that we have to take care. So in case of Rx and Rz, this part is essentially the same. They are more or less the same. Just it's only their position that is changing. That's about it. So in this regard, the correct answer is option 2. That is indeed the correct answer. Yeah. So with that, we end up. We'll wind up this session. It has been a long session. This is only supposed to be a 2-hour session, but I suppose we have covered around 2.5 hours. But then again, thank you all for staying with me until this session.
Thank you very much, sir.
Huh?
Thank you, sir.
Yeah, thank you. Thanks. It was my
Thank you.
pleasure.
Thank you. Thank you.
Next slide, sir.
Yeah. Any questions?
If possible, please share slides, sir.
Yeah, I'll share the slides. I just need to find out a way to extract this recording.
Okay.
I'll try to upload it today itself. It'll be shared in the course page itself. The slides as well as the recordings will be shared.
Okay, sir. Okay.
Okay, so thank you for joining. Maybe from next week onwards, I'll try to keep it within 2 hours.
Thank you.
Okay, sir.
Okay, thank you.
Okay.
Thank you.
So could you move over to the question 1 to 5 once again? I have to just look into it.
Which one? Questions?
1
thank
to
you.
5.
Questions 1 to 5. Yeah. I mean, the slides will be shared. Maybe if you want me to clarify that, I can do that now. But if you simply just want to have a look at it, you can do that later as well, because anyway, the slides are going to be uploaded.
Okay then. I'll check it from there. Thank you.
All right. So you guys can also reach me through the discussion forms, right? There is also a discussion form there's a Google discussion form. So if you have any doubts, you can post it in the discussion form. And if I notice any questions, I can answer that as well. All right. So thanks again. I shall stop sharing my screen. Okay, thank you.